In this chapter, we will be exploring exponential functions. In this lesson, we will be looking at financial word problems.
Okay, so in this particular lesson here, as indicated, we're going to take a look at some financial applications here of exponential functions. And specifically, we're going to look at the compound interest equation. Okay, it's just a special exponential function, so you'll notice all the pieces are very similar to what we've looked at before. But it's actually a really useful model for looking at investments, looking at money, and other populations. I appreciate the fact that that's included in there because it is a fairly good model for looking at how populations grow, right? So, because money behaves a lot like, populations of biological entities here. The more of them you got in an area, they tend to grow. There tends to be more of them after a little while. The more money you got in a specific area here, in a bank or whatever, after a while you tend to have more money, okay? So, and specifically what makes this one a good application here, or a good equation for this, is that when you put money into an account, when you earn money, the next time you earn money, you earn interest on the interest that you earn. So every time you earn interest, you're earning it on top of the interest. So it compounds. That's why we use that word there, okay? So anyway, here's the function, here's the model. A equals P times 1 plus I to the n. So A is the initial amount. Now compare that, or not, sorry, A is not the initial amount, it's the final amount. Compare that to the exponential function. So where Y is the value of the function, A is the amount after you've applied all the information that you have for the other variables here. It's what we call the accumulated amount, or the future value of that account there. This is the A that I was thinking about here. The P refers to your principal amount, the initial amount that you enter in here. It's taking the place of that little a. Think of that as the y-intercept of the graph. Okay, but it is the initial amount here. B is going to be this 1 plus I, and we've already talked about that in previous lessons here. Okay, so in this case here, because I'm separating the 1 and the I out here, what I is specifically here is the rate of growth. Okay, it's the interest rate. It's the percent change in the value here. If I is negative, then you're losing money. If I is positive, then you're gaining money here. But more specifically, in this particular case here, we have to be clear that I represents the interest rate per compounding period. Okay, so the number of times that interest gets calculated and added to your account, the length of time that the bank waits before they do that, that's called a compounding period. Now, they might wait the full year, but they might not. They might wait for fractions of a year. So what happens here is our interest rate needs to be per compounding period, and then N, in this particular case here, is not the number of years that have gone by, but the number of compounding periods. So you need to be thinking about it in terms of compounding periods, not years that have passed in this particular application. So now let's just take a quick look at the relationship between I and N, because we've just hinted that it's a little bit more complicated than just yearly. If it is yearly, then you're just like dividing the interest rate by 1 and you're multiplying the N by 1, because it's just happening per year in that case. But semi-annually, you divide the interest rate by 2 and then you'd multiply the N by 2. Now in this case here, think of it like this. This is supposed to be the number of years. Actually, this is maybe how you should think about it. This should be the number of years, and if you multiply the number of years by 1, there you get N. If you multiply the number of years by 2, then you get N, because N is the number of compounding periods. If you multiply the number of years by 4, then you get N. Then you get N here. So semi-annually for 2 years. Let's just talk about it really quickly conceptually. Let's say that you're getting, let's not use 4, let's use 6%. 6% compounded semi-annually. So what they're going to do with that 6% is they're going to divide it by 2. So in June you're going to get 3%, and in December you're going to get 3%. And how many times does that get compounded per year? Well, you're going to multiply that the number of years by 2. So if, let's say that's in there for 5 years, it will have been compounded 10 times, and would be 10, because you're going to compound it twice a year. Let's say it's quarterly. Okay, let's say the same scenario here. Let's say you got 6% here. If you're compounding it quarterly, you're going to divide by 4. Now that means, okay, you're gonna compound it in March, or sorry, it's going to calculate in March, in June, in September, and then in December. There, you're going to do it 4 times a year. Okay, which is what this is saying here. So now let's say if it's in there for 5 years, it has been compounded 20 times. That's why we're multiplying the number of years by 4 in this case to get the number of compounding periods. And you can even do it monthly if you want. Okay, there's a number of different ways that this could happen. This is just the really, really common ones. Okay, so now let's take a look at some specific problems and utilize this compound interest equation.
If $4,000 is invested for 5 years, determine the total amount at each interest rate after 5 years.
All right, so let's talk about what would happen if we had it at 8% compounded annually. Okay, so here's our A equals P1 plus I to the N. So we're going to figure out our final amount here. Well, we're told in the question that the initial value is 4,000. In this case, we've got 1.08 because it's 8%. Now, and I'm going to leave it as 0.08 because it's compounded annually. Okay, so I don't have to do anything to that. It's in there for 5 years, so compounded annually for 5 years, N is going to be 5. There'll only be 5 compounding periods. So now, I'm just going to go to my calculator and enter that in. Okay, so 4,000, 1 plus 0.08, and then to the power 5. So at the end there, I would expect to have $5,877.31. Okay, so we would have $5,877.31. Now compare that to this question over here, 10% compounded semi-annual. A is equal to P1 plus I to the N. I'm going to keep writing this. We're looking for the accumulated value. Our principal value was 4,000. Now, this time, because I'm looking at 10% compounded semi-annually, this would be 0.1, but I'm going to divide by 2 because it's semi-annual. So essentially it's going to be 0.05 in there. Now, it's going to be in there for 5 years, but compounded semi-annually means it's going to be compounded 10 times, twice a year for 5 years. Now, let's go to our calculator. So this will be 4,000, 1 plus 0.05. I already know that 0.1 divided by 2 is 0.05, to the exponent of 10 for 10 compounding periods. So I would expect to have at the end there, well, that's substantially more, $6,515.58. Okay, now granted that's because I've got a larger interest rate, 10%, but also that compounding semi-annually means there's a little bit more money in there by the middle of the year that's earning interest towards the end of the year. So it's a little bit faster, the growth there. Let's take a look at this. 9% compounded quarterly. Here we go. A is equal to P1 plus I to the N. Again, $4,000 we throw in there. Now, we're going to take this 9%, I'm going to divide it in 4, and my exponent here over 5 years, though, compounded quarterly, 4 times a year, this is going to be 20. 20 compounding periods. So let's go for it. 4,000 times 1 plus, I'm just going to let the calculator do it this time, 0.09 divided by 4, and raise that to the exponent 20 for 20 compounding periods. $6,242. And just a little bit here, $6,242, and what did I get? 4 cents. Oops, sorry, you can't see that. Okay, so you go, so, I mean, a little bit more. I mean, the interest increase here was just 1%. But that's a substantial increase when I compound it quarterly there. It's interesting. 6% monthly. It can be interesting to see what happens when the interest rate drops, but the compounding goes up. So, well, I'll just enter it in there. 4,000, we already know what it's going to be. 4,000, 1 plus 0.06, but I'm going to divide that by 12. Okay, I'm chopping up that interest rate into 12 bits. Now, monthly for 5 years, that's going to be 60 compounding periods. 60 compounding periods. So here we go. 4,000 times 1 plus, well, 0.06 divided by 12. Okay, close those brackets, and we're going to raise that to the 60. 5 years, 12 times a year. 395.40. Okay, whoops. So now that is less, everybody. That is less than what we have had before here. But it's interesting how that compounding monthly, okay, how it changes things. Actually, if we were just to let's do it like this, just for fun. Let's throw 6% in there annually. So 6% annual. I'm just going to take that thing back here. That would just be 5 times. And I'll just delete that, divide by 12. I just want to compare this. Watch what happens when you compound it monthly compared to annually. Okay? Okay, maybe it's not a huge difference there, but if you let that go year after year after year, that's going to make a difference. That's interesting.
Brittany invested $3,000 at a rate of 3.5% per annum, compounded semi-annually. How much will her investment be worth at the end of 4 years?
Okay, so here we go. We're going to try to figure out how much it's worth at the end here. So we have a principal of 3,000, 3.5% per annum, but it's compounded semi-annually. So it's going to be 0.035 divide by 2. And we want to know how much it's going to be worth at the end of 4 years. Now, compounded semi-annually at the end of 4 years, that's 8 compounding periods. So now let's go to the calculator. Okay, and we get 3,000. This is just entering it in. Plus 5 times 1 plus 0.035 divided by 2. And then we're going to raise this to the power of 8. Okay, 2 compounding periods per year for 4 years. So this will be worth, okay, according to the calculator here, what did I get here? $3,446.65. That's how much it's going to be worth.
Determine graphically how long in years it will take her investment to reach $5,000.
Okay, so determine graphically how long it'll take to get 5,000. First what I'm going to do is enter in my function here. So first of all, 3,000, 1 plus 0.035, okay, over 2. Now, up here, I want to know how long in years it will take. Well, now, my exponent here has to be in compounding periods. So the number of years, if I let x be the number of years, then what I got to do to x here is multiply that by 2 so that this is the number of compounding periods, but x is the number of years. Okay? Now, down here I'm going to let y2 is equal 5,000. I'm going to look for where those things match. So I'm going to go to my calculator and I'll enter in these 2 functions here. So 3,000, 1 plus 0.035 divide by 2. Okay, close brackets, to the exponent here, 2x. And again, x will be the number of years, and then 2x is the number of compounding periods. Down below, I'm going to put the 5,000. Now, if I graph that, right now I'm not going to see anything because my window settings are just my standard window settings. Okay, I don't need time to go into the negative, so I'm going to let x min be 0. I also don't need the money to go to the negative, so I'm going to let y equal 0. Y min equals 0. Now, I don't know how long it's going to take. But I do know that my x max here, if I'm talking about this money here, it's got to be bigger than at least 5,000 because 5,000 is that borderline that I'm looking at here. So let's make it 6,000 just for out of interest sake here and see what we get. So there's the 5,000. That's the thing I'm looking for here. So it's going up, up. Okay. My function, the blue function, is increasing, but it didn't quite get to it. So let's make that a little bit bigger here. 10 wasn't enough. Let's try 20. And there we go. We got our point of intersection. That's what we were hoping for. So now I'll go into my calc menu, second trace, down to the intersect feature. I am on the first curve. That is, in fact, the second curve. I'm going to press enter to get past the guess. And I get that this value is 14.7. Okay, so x is going to equal 14.7 years. Now, determine graphically how long in years it will take your investment to reach 5,000. Okay, well, let's think of it like this. 14 years passed. I'm 0.7 of the way through the next year. This is really going to be approximately 15 years. This happens in the 15th year that we get to that $5,000 mark.
The value of a type of robotic technology depreciates 25% per year. How many years to the nearest whole year would it take for the value of the robot, which is initially set at $575,000, to depreciate to a cost of $25,000?
Okay, now in this question right here, we're not seeing any kind of compounding effect happening in this particular one here, just that we got some depreciation here. So we've got the value here, A is equal to P1 plus I to the n. I'm still going to use the compound interest equation here. But notice we're told that the robot here is initially costs $575,000. So there's my $575,000. We're looking at how many years it's going to take to depreciate to $25,000. That's a significant depreciation here. Now, this question here is really more about using this compound interest equation, the base here, because if it's depreciating by 25% per year, then really what's happening here is we are losing that 25% per year. So that we got a negative 0.25 there. Now, we're assuming this is happening per year, so n is going to end up being the number of years. So now for me to answer this, what I got to do is go to my calculator. I'm going to graph y1 will be equal 575,000, 1 minus 0.25 to the n, or to the x here. Then y2 will equal 25,000. Okay, so now I'm going to go to my calculator and I will enter this all in. So in y1, I said that I was going to have 575,000 times 1 minus 0.25. Now I could have done that. I mean, I know that that's 0.75, but whatever. Put that to the power of x. Down here I'll have 25,000. I've entered that in here. Now, when I graph this, I'm not going to see it. I know that already because my window settings I put back to the standard settings here. I know that it doesn't make sense to talk about negative time or negative money. I don't know how long it's going to take. That's the one I'm going to play with here. But I do know that my max here has got to be bigger than 10, particularly if that other function is starting at 575,000. In fact, since I know that's the beginning value for that, I'm going to actually have the graph start here at 575,000. Now, I hope that doesn't overwhelm my second graph there. Like, I hope I can see it clearly. Let's graph this, see what we get. Okay, I do see it clearly. It's right near the bottom, though. That thing drops down. Oh, hey, it looks like it touches there. I'm not quite sure, though. I'm going to increase my x max here. Let's make it 15. That should be enough now. That exponential function drops. Okay, good. We got a clear intersection point there. So let's go now check it. So second trace gets us into the calc menu. Number 5 is intersect. Is that the first curve? Yep. Is that the second curve? Yep. And I'm okay to let it guess that. And so now we get, what is that, to the nearest 10th, 10.9 years. So n here is going to be 10.9 years. I'm just going to double check that, look a little closer. Yeah. Which means, hey, this is really, that happened in the 11th year. So it took 11 years to get down to $25,000.
A coin collection worth $1,000 appreciates 2.5% per annum. Determine the exponential equation and then graphically determine how long until it's worth $2,000.
Okay, so the first one here, determine the exponential equation. So here we go. I'm gonna work with the compound interest equation again, just because I like working with it. It's a good one. So I want to know how much it's worth. That's my A value here. It starts at 1,000. That's my principal. It's appreciating, so it's going up in value 2.5% per year. Now, per annum. That's what that means here, per annum. So I'm going to add to that 100% of its value, 0.025. And because it's going up just per year by that, I'll just put an n there, and that's going to refer to the number of years. So graphically determine now how long it takes to be worth $2,000. So I'm looking for where the final answer here is 2,000. I want the accumulated value to be 2,000. So what I'm going to do here is I'll graph these two. So I'll graph the model here, 1 plus 0.025 to the n. And then my second one here will be 2,000. We'll just go to the calculator. Let's do it. Okay, so my first equation here was 1,000 times 1 plus 0.025 to the power of x and my second one here will be 2,000. Now I already know that my window settings won't work here because I put them back to the standard window settings. So I'm going to change the X min to 0 and the Y min to 0 because it doesn't make sense to talk about negative time or negative value. X max being 10, hey, that might work. But my Y max has got to be, it's got to be at least bigger than 2,000. The ring is growing in value. I'm looking for where it hits the 2,000 mark. So I don't know, maybe let's put 3,000 up there as my max. We'll see what happens. Let's graph that. Okay, well, I can see that the blue graph here, okay, the model here is growing. It is going up, but it's going up slow. So I got to make that X max a bit bigger. In fact, I got to make it substantially bigger. Let's make that 50. Let's see if that does it. Okay, that's looking a lot more promising. Okay, good. Good, there we go. So we do have a clear point of intersection. So now I'll go into my calc menu, second trace, number 5. Oh, and it's right near it because the intersection is close to the middle here. So enter for the first curve, enter for the second curve, go past the guess, and we get 28.07. So X was equal to 28.07. So now this happened very, very early in the 29th year. Early, very early. In fact, you might say this was about approximately 28 years. That's another way to think about it. It happened just after 28 years was accomplished. It is in the 29th year. In the 29th year, but it really is about 28 years that it took for this to happen. I apologize if the way we were talking about time here is a little bit confusing. It really is. And you'll find that questions ask you to interpret it one way or the other. You have to be very careful when you read the questions to know how you're expected to answer them.
The table below shows the value of an antique ring over time. Determine a regression equation, find the rate of increase, and then determine how many years it will take for the ring to be worth $2,000.
All right, here's an interesting question because of the fact that we have to do a regression here first. So here we go. First of all, determine the regression equation. Well, what we got to do here is first of all put the data into the calculator. Okay, so I press my stat and enter to get into there. Now I've already got data in there, so I'm going to go up, press clear and then enter, press clear and then enter. There we go. So now I've got, here's my data. Now here's my list 1. 0, 1, 2, 3, 4. So 0, enter 1, enter 2, enter 3, enter 4, enter. There's my 4. My 5 values, I should say. Now my list 2, okay, and it's 800, 841.60, 885.36, and I can see right now that I did not press enter up there to make that work here. So let's do it again. 800, enter, 841.60. See, it's not doing that point there. 0.60, enter, 885.36. There, that's looking better. 931.40, enter, 979.83, enter. There we go. So now my data's in there. I am going to quit to get out of here, and now I'm going to do the regression equation. So remember how I do that. I press my stat button, and my regression equations are all in my calc menu. And specifically, my exponential regression is down here at 0. Now, again, for a number of you at this point here, you're probably going to have to go second 1 to get list 1, comma, which is just above the 7, second number 2 to get list 2. I don't with my calculator because it's anticipating that already. So yes, yes, and then come down here to calculate. And here's my regression equation. I'm starting at, now, take a quick look at this. It seems pretty clear that I should be rounding. This should be 800 times 1.052. Okay, so let's enter this down here. My regression equation is going to be y equals 800 times 1.052 to the x. Okay, so this is the value of an antique ring over time here. what is the rate of increase? Okay, now that's when I come to this here. My rate of increase is going to be from this. It is going up, okay? But remember how I do that. What I would do is I would take that B value, 1.052, subtract 1 from it, and what you're left with here is that 0.052, which means what we get here, our rate of increase, is really therefore 5.2%. Okay, every year I'm getting 5.2% more than the whole value was before. Now, here's the more interesting question. How many years will it take for the ring to be worth 2,000? So I want the y-coordinate here to be worth 2,000. So what I'm going to do is I'm going to graph this. Okay, here we go. Now the fun begins. So I have done the regression equation. That's done. Now if you haven't done this, then you can't follow the next step here. Okay? You have to have done the regression here. Now I go into y equals. I want to put the regression equation here. Don't write it out and enter it into your calculator. Let the calculator do that work for you. So to get that in here, I'm going to press my vars button right here, vars. It's going to open up a whole bunch of options here, and I just did a statistical thing. So I'm going to press number 5, and that opens up my statistical menu here, and EQ is the one I want. There's my regression equation. So I'm going to press enter. The calculator drops the regression equation there. Perfect. Now, I'm going to be interested in where this thing is equal to 2,000. So what I'm entering into the calculator here, y1 is going to equal, now I'm not going to put right down here exactly what went in there. This is just rounded. I know that I used all of the values that the calculator offered me, but that's the rounded value. y2 is going to equal to 2,000. Okay, so down here 2,000. Okay, now when I graph this, I could let the calculator choose the window settings for me, but I've done this enough already that I kind of have a sense of where this is going. I'm just going to go to my window. I haven't changed it from a previous question here. My x min should be 0, my y min should be 0 because negative time, negative value doesn't make any sense. I'm going to put that back to 10, the x max, because I don't know that that's wrong. 10, why not? Between 0 and 10 years? Maybe. Now, what should my y max though be? Well, the calculator here, this function here starts at 800 and goes up, and I'm wanting it to get to 2,000 here. So 2,000 is kind of my limit here. So from a previous question I have 3,000. Actually, that's not a bad place to stop. So I'm going to let that sit, graph that. So there's my ring value in blue, and there's my goal, the red. Yeah, and just like a previous question, that 10 years just isn't enough to do it. So I'm going to make that bigger. Let's make that 20 years. Maybe this will do it. Closer. And look at that. So it happens just prior to the 20-year mark. Now let's go figure out our point of intersection. So second trace to get into the calc menu. Intersect. That is the first function. That is the second function. And guess that if you want. And now I get 18.07. Okay, so x is equal to 18.07. Now, how many years does it take for that to happen? Okay, well, it took just slightly over 18 years. So this is approximately 18 years to get to that point here. But it happened in the 19th year. So I'm throwing down both options there. It took approximately 18 years, because if you round that to the nearest year, it happened just slightly over the 18-year mark. Okay, kind of your 18-year anniversary happened, and then just after that, it hit the $2,000 mark here. So that happened in the 19th year. Depends on how you're being asked that question, how you should answer that.